time. I am Dr. Matthew Richardson, and today we're going to be having some fun with particle physics. But before diving into today's fun, physics fun, let me first verify that I'm actually streaming, as I always do with everything. So I'm going to go ahead and log on to Twitch and see what's going on. I'm hoping that today's taking my screen. We'll see. Alright, so OBS software says I am live. What do you have to say about this? This is also showing I'm live, but however, there appears to be no one here.
All right. Let's do this. I'm going to refresh the page to see if I can view comments. I seem to always have a problem with Twitch's chat every time I start one of these streams. And so let's see if the problem gets fixed. Maybe let me do this. All right, so I'm gonna kill this browser. I'm gonna reopen it. I'm gonna navigate to Twitch again. Great, I'm already logged in. Oh, there we go. I think this is now working. I can see that people are here. Let's go ahead and pop out the chat. So, and just a quick hi to everyone. Hey, Cosmic Lettuce. Hey, Larry of the G Cloud. The audio is low. Can you guys hear me now? Is it a little bit better? Crackly and faint auto. Okay, let's see what I can do about that. So for everyone who's currently here, are you all having the same problem? So far, too. Okay, better. All right, so I did nothing. So apparently that must have been like the internet connection or something like that. Maybe it's better now. I hope it stays this way. But let's go ahead and get started before things go bad again. All right. So let's see. So I'm going to see if I can modify my sound settings as Jay has suggested. Or Joe, I'm sorry, not Jay, but Joe, as Joe has suggested. Um, let's see, audio. Okay, Guido can hear me. Cosmic Lettuce can hear me. Hey, Susie. So you guys can hear me. Let me just get started with today's stream. I'm not gonna mess around with the settings if everyone's saying it's okay. All right, so I'm gonna kick this off by talking a little bit about the standard model. As some of us know, or maybe all of us know, the Standard Model is basically our view of what elementary particles, the very smallest building blocks of matter, look like. From my understanding, for the most part, we've been able to construct this particular model of physics over the past century or so. And to date, it's composed of 17, with the inclusion of the Higgs boson, its very recent discovery. It's composed now of 17 um, elementary particles. And so what I've chosen to do is talk specifically about one of those particles. All right, so I'm going to assume, and this is a little bit off topic, but I'm going to assume it's my connection because I'm looking at my OBS software and the little light that corresponds to how the stream is doing, it's been changing colors from green to red. So hopefully I don't have any issues with the connection, and that at worst it's just the sound issue, and that even that's minor. But yeah, fingers are crossed. But yeah, so today we're going to be focusing primarily on the muon. Oh no, Cosmic Lettuce lost me. Am I back? All right. I'm hoping that I'm back for you, Cosmic Lettuce. Um, yeah, let me go ahead and continue. So first things first, let's go ahead and switch the scene to, well, part one of today's problem. All right. So my question to you guys is, given the given the given the muon particle, it undergoes a specific type of decay. So that means that it starts as a muon, and it converts itself into another a completely different set of particles. And the reason why it does is because it's not stable. It prefers to go to a more stable set of particles. And so my first question for you guys is, and as I said, this is part one. Which of the following particle interactions or decays is the valid interaction for the muon decay? The muon minus decay. There's also a muon plus decay, but that's the antiparticle for the muon, and we're not going to get into that. But what do you guys think? So the muon is an unstable particle, and it decays into more stable particles. And I'm asking you, of the three particle equations that I've given here, which one do you guys think corresponds to the correct decay equation? All right. All right. Larry of the G Cloud says, I do not know. That was unexpected because typically Larry answers all of my questions correctly. All right. So I'm just going to go ahead and give you guys the answer. The correct. Okay, so Larry just chose one. Perfect. The first one. All right. So I'm gonna go. I'm just gonna assume, because I'm not seeing anyone else type right now, that you guys probably just don't know, or you're looking it up. But the correct decay method for the muon minus particle is the third equation. And the way in which we're able to tell if this is the correct equation is based off of a few set of laws that have been developed for particle interactions. These are conservation laws. And so with the three equations that are given, one particular thing that has to be conserved is what's known as lepton number. So let's so Larry says duh. So let's quickly go back to our standard model. And what we see is at the bottom left-hand portion of the image that's shown, these 6 particles that are colored green correspond to the leptons. So whenever you have a particle interaction, Upkeeper of Maps is going to say 3. Good job. That's perfect. I'm happy to hear that, actually. So because 3 is the correct answer. And so the one thing that has to be conserved. Oh no. Sorry, I stopped for a second because I'm seeing my internet connection is like fluctuating crazily. But and so if you notice at the very bottom that we have our leptons, and what has to be true for particle interactions is that the number of leptons on the left-hand side of the equation must be equal to the number of leptons on the right-hand side of the equation. And to be more specific, if I have one muon lepton on the left-hand side of the equation, I must have the same number of that particular type of species of lepton on the right-hand side of the equation. Yeah, a third is not. It's not bad odds, right? That's better than me actually adding another equation, right? Making it into a fourth. Ah, the 2 neutrinos threw you off. Okay, that's perfectly okay. Um, and when I first started, when I first started learning about particle physics, the 2 neutrinos threw me off as well. I was like, that can't possibly be the answer. But let me go ahead and explain the reason why the third equation actually works and why the other two don't. So with the first equation, if you notice on the right-hand side of the equation, there is no muon lepton, whether it be the actual particle itself or its neutrino counterpart. So number 1 is kind of just automatically thrown out. The same with number 2, actually, with the second equation. There is no muon lepton, again, whether it be the actual particle or its neutrino. But also, on top of all that, we have this proton being thrown into the equation. And so charge, which is also one of the things things that has to be conserved in particle interactions, is not being conserved in this particular equation. And so as we move to number 3, we have of course the muon on the left hand side of the equation corresponding to its lepton number being 1, but then we have its neutrino counterpart, the muon neutrino. So because the muon neutrino is on the right hand side of the equation, it balances out as far as its lepton number is concerned. But now we have to reconcile the fact that we now have an electron and its antineutrino, an antineutrino electron. And it just so happens that whenever you have antimatter particles in a particle equation, they count as a negative number, or they count as a means of taking away lepton numbers from the equation. And so it just so happens that the electron and its antineutrino electron, their lepton numbers cancel out, and makes everything happy as far as conservation laws are concerned. Oh, I'm sorry, I didn't switch the scene, did I? I apologize for that. Thank you. I will make that's actually the very last time I'm going to end up showing the standard model. From here on out, we're going to actually work through a problem. So that's the explanation behind the reason why equation number 3 works. And the reason why I bring up equation number 3 is because we're going to be talking about, of course, as the title suggests, muon decay. So let me go ahead and bring up what I want to discuss with that. Oh, that's right. I end up. All right, let's do this. Give me a second, guys. you're going to see some weirdness on the screen. That is that my PDF is going to shrink for just a brief moment so that I can bring back some stuff. All right, let's minimize this. Let's do this. There we go. And everything should be just fine now. All right. So, the second part of today's exercise, or today's stream, is the following. We are now going to go ahead and calculate the maximum kinetic energy of the electron in the decay method that I'm showing above, which I'm now actually restating in the equation at the very bottom. And so, because this is a particle interaction, we want to be able to use what we know about physics, in particular what we know about particle interactions in physics. And in general, what we can typically use are two very useful laws of physics, those being the conservation of energy and the conservation of momentum. Let's see if I can make a slight modification to this so I can always bring that back. All right, that'll work. Let me see how it's affected the stream. Sorry guys, I had to modify my PDF viewing area. Let me see how it's okay. It did change that. That's cool. I can fix it. All right. This way things will work out. Actually, Larry the G Cloud, I'm trying to think about that. I'm pretty sure it does. Wait. Muon decay for cosmic rays. So I know about in cosmic ray air showers, we can have pion decays. And of course, I know that as far as cosmic rays traveling through the universe, we can have specific type of decays. But I'm not gonna. I don't really remember seeing too much about muon and specific muon decays for cosmic rays. But Cosmic Lettuce asks if it comes back to mind, I'll let you know, Larry the G Cloud, or Larry, excuse me. It's a lot easier to say Larry versus saying the entire name. So let's see, Cosmic Lettuce. Please remind me, Matt. The arrow pointing to the right means decays too, right? So yeah, the arrow pointing to the right indicates that the interaction has occurred, and so you start off with the particles on the left hand side of the equation, and then the arrow indicates that an interaction has occurred, and that you end up getting these resultant end products. All God's children are ions. Oh, but yeah, that's what the arrow indicates, that you started with one condition and now you've transitioned into another after some interaction has occurred. So from here, what we can do is we can actually employ our conservation laws. And we'll start off by employing the conservation of energy to be able to start to determine what the maximum kinetic energy of the electron will be in this decay. So let me go back and pull up my LaTeX text editor. So I'm going to go ahead and type, and I've modified things for this stream so that you guys can have the maximum viewing area. I've removed the actual text editor so you can see just the end product, which is going to show up on the PDF. So I'm going to start off with conservation of energy. Okay, that works too. Cosmic definitely works. Oh, no worries, Peter. Oh, wait. I'm sorry. I'm sorry to kind of like go away from the stream, but when you say you're done, what do you mean by done? Am I confusing you, or are you referring to something else? Yeah, guys, if whatever I'm saying is not making sense, by all means ask. But yeah, we're talking about now conservation of energy for this particular interaction. And so what we end up getting is that before the interaction occurs, we're just going to assume, even though it doesn't state this in the question, we're going to assume that the muon itself is at rest. So the only energy it will have is its own intrinsic rest mass energy. So give me a second to type this up. I realized that it actually was kind of useful to have this particular screen shown as well. That way you guys can see me actually working and typing this up. Ah, Michael T. Mayer, what's up? So your statement, we sum the masses of the new particles, subtract from the masses of the muon, and the difference is kinetic energy of the new particles. Nice. So if I'm not mistaken, Michael T. Myers may have already like outlined everything that we need to do so far. So at the very moment, yeah, we're gonna first set up the equation, and that equation will basically be composed of the energy before and after the interaction. And so just as Michael T. Mayer was stating, we want to be able to sum the masses of the new particles, and that's going to, or sum the rest masses of the new particles. Well, I don't think I wasn't going to actually write that out. I was going to write out the total energies for both sides of the interaction. And so to write those energies out, we have to consider the fact that for the muon, it has only rest mass energy. And so we'll currently go ahead and write that out, which is going to be its mass. So yeah, I think of course Michael already knows the answer. Or at the very least he knows the steps of how to get to the answer already. Which is a good thing because you can keep me honest. Alright, so we have M mass of the muon times C squared. And we're gonna say that this is equal to. Now, as far as the resulting particles that we get from this interaction, of course they'll have their own rest masses. However, they'll also have kinetic energy as well. Can or might not have kinetic energy. In this case, because we're looking for the maximum kinetic energy of the electron, that would have to mean that all the particles will end up having some bit of momentum to them. So, sorry guys, let me quickly look at my notes. I wrote this up before I actually got this started, and so I want to. So what I'm going to want to do is write out the total energies and subtract the rest mass energies for each particle. All right, so let's go ahead and do that. SQT. And so by doing this, though, I'm doing exactly as Michael stated earlier, which is I'm solving for the kinetic energies of each particle. So to get the total energy of each particle, we're going to end up, you know what? I'm going to go ahead and modify my OBS software so you guys can see me doing this actually. Let's see, this is the latex editor. There we go. That actually might be a cool place to keep it. For now, I'm just going to keep it up here, and I'm just going to increase the size. There we go. That's a lot better, actually. So we're employing conservation of energy, which in this case, the total energy before the interaction is equal to the total energy after the interaction. And we basically end up getting that the energy before the interaction is just simply the rest mass energy of the muon, and that the energy after the interaction is going to be the total energies of each individual particle minus their rest mass energies. Square root, and I'm going to try to type up quickly because it's now like 12:30 and I know that typing takes up time. Plus m underscore, I need the electron for this, MC, and that's going to be squared. This is going to have to be the momentum of the electron times c, the speed of light, and I want to subtract from this the rest mass energy. Let's make sure that this is going to come out in the correct way. So far, that looks good, actually. Does this work, Keeper of Maps? I'm sorry. All right, so that's the equation so far, but now I have to add all the other terms as well. So to do this, it's actually quite easy just to simply copy and paste and modify. So let's see, I'm going to go ahead and take this. And let's put brackets around it actually. Because we should get one term for every single particle in our equation. Plus and let's see, let's make this easier on myself. I'm going to go ahead and I have the electron. I need this one, which is the anti-neutrino electron. There. And I need the muon neutrino. Here, and here. Let's go ahead and typeset. Please work. Okay, that is very long. So long to the point where it's hard to see the entire Let's do this. All right. I think that makes things work. And so as you can see, conservation of energy, we should have a term for each particle in the actual interaction. On the left-hand side of the equation, all we have is the rest mass energy of our muon. And on the right-hand side of the equation, each term within the brackets corresponds to the kinetic energy of each of the particles that were generated. All right. So as we continue from here, let me make sure I'm keeping up with comments. All right, so Leary, you say what P? Is there a P? Is there a P? Did I put a P in here? Oh, what is the P? I'm sorry. Yes, I did. So the P's in the equation represent the momentums. So, for example, P sub E represents the momentum of the electron once these particles have been generated. And the P for all the other P's correspond to momentums for their individual particles. So I'm going to go ahead and continue with this, and we're going to modify it. We're going to go ahead and modify. Well, we're going to go ahead and leave it like this, actually. Sorry. We'll leave it like this for now. So this is the actual conservation of energy equation for our interaction. Now note, we can also determine what the energy would be for the particles that are being generated. That is, what the total kinetic energy will be for the particles that are being generated. Now we can do this using what's known as the Q value. And this too also is based off of conservation of energy. So, and it's really based off of the fact that, and I'll go ahead and get to typing while I talk. It's really based off the fact that as these particles are being generated, the sum of their rest mass energies will actually be lower than the rest mass energy of our muon. And so the difference between the rest mass energy of the muon and the sum of the rest mass energies of the particles that are being produced will end up being the total energy that's going to be invested into the kinetic energies of each particle. That is, of each of the electron and the two neutrinos. So this is also based off of conservation of energy, but it's known as the Q value. So no indent. Indent, and so I'm going to go ahead and put Q value. Starting to wonder though, I might actually be able to get away with using the Q value. I saw for the momentum. Yeah, actually guys, let's not even worry about the Q value. We can actually do without it. Let's just go ahead and right now take into consideration that we're actually looking to solve for the maximum kinetic energy for the electron. So we can actually continue on and just start talking about how conservation momentum is related to this problem. Have to think about that for a second. And this is actually a problem that I've pulled from my physics textbook. And and I wrote some quick notes prior to our stream today. I mean, I've worked many particle interaction problems in the past, so but yeah, we could do without the Q value though. All right, so conservation momentum basically tells us that the momentum before, and I want to use an arrow above to represent. So why is momentum multiplied by c? So the reason why the momentum is multiplied by c is because, so I think someone already answered actually. Rest mass, that's the rest mass, right? So if you want to be able to get energy or units of energy, you'll need a mass times the velocity squared. And so your momentum will end up being, even if it's relativistic, in general, the units for your momentum will end up being mass times velocity. However, you're missing that extra factor of velocity, and you get it by multiplying the momentum times c. P is equal to mv, so pc quantity squared is equal to, basically you're going to get energy squared, right? So yeah, pc quantity squared is your energy squared, and it's kind of like looking at, yeah, I mean, in special relativity, and I'm responding to Larry's statement. In special relativity, the idea is that particles in general will never actually reach the speed of light. In general, and I think that actually Michael and I have had a discussion about this in the past, and he ended up correcting me on something as far as general relativity is concerned. But I think, and if I'm wrong with saying this, someone please correct me. But I think in general, though, you don't expect for particles to be able to reach the speed of light. But yeah, let me go ahead and continue though, because it's almost 12:40 now, and I need to get this finished. Um, so right, so we end up getting the momentum before. Can you guys see everything that I'm? Yes, you guys can. Perfect. All right. So we end up getting that the momentum before has to be equal to the momentum after. What I really want to be able to do is represent this as a vector. Let's see if this actually helps. Oh, I said arrows. Let's see if this works. Okay, that does not work. Give me one quick second, guys, because I want to be able to represent the momentums as a vector, because the conservation law applies to the momentum as a vector and not just simply its magnitude. So LaTeX arrow over text. There we go. All right. Sorry, guys. I got it now. So let's correct this, and that should do it. I hope. All right. So the fact that I have an arrow over the p, where p represents momentum, lowercase p represents momentum, um, indicates that it's a vector. All right. And if there is no arrow above it, I'm simply referring to the magnitude of the momentum. And so this is actually the conservation of momentum in a very short and simplistic statement. And that is, the momentum before an interaction is equal to the momentum after the interaction. And given that we know that the muon was at rest initially, or we're assuming that it's at rest, that means the momentum before the interaction is equal to 0. So we end up getting 0 is equal to the momentum vector after the interaction. Let's kind of scroll that up so you can see it. All right. And so what we also know is this, though. The momentum after is actually going to be composed of the individual momentums of the particles that we're producing. So let's go ahead and make that or add that bit of information into our equations here. And so now we have this is going to be equal to I'm sorry guys, I'm trying to do this quickly because I know the time is kind of winding down on me. All right. Nearly got it done. And lastly will be the momentum for our muon neutrino. All right, so let's see. Google Chrome. Particle with mass. Sorry, now I'm looking at comments to try to catch up here. Yeah, keeper of maps. Yeah, I definitely believe you on that. Hey, DSOC, or DISOC, if that's correct. I hope I got that right. Yeah, this is LaTeX. So I'm typing everything in LaTeX right now. Particle with mass. Yes, massless particles, of course, like photons, can move with at the speed of light. So as far as I know, there's two things that move with the speed of light. Photons and gravity waves. Gun split. Well, Cosmic Lettuce, thank you for stopping by and seeing the stream. So I'm using Tech Shop. Yeah, I'm using LaTeX, but specifically I'm using Tech Shop. Okay. Let me go ahead and continue from here. So so we've gotten this far, and I need to really rush. Actually, this stream might go a little bit over time. I hope you guys don't mind. But now that we've gotten to this point, we've established now that the sum of the momentums must equal 0. The sum of the individual momentums, that is, the sum of the momentum of the electron, the momentum of the anti-electron neutrino, and the muon neutrino must all equal 0. And so now we can start getting an idea of how we should go about trying to solve for the max kinetic energy given this information. So no indent, and I'm going to quickly write that in order for us to get the max kinetic energy, this implies that we also need to solve for the max momentum of the maximum momentum of the electron, because the two are essentially tied to one another. And we're not even worried about the actual vector momentum. We're worried about its magnitude. I hope this comes out right. It should. Where is it? And it's actually a good thing that we're only concerned with the magnitude of the There we go. Perfect. All right, so we're going to go ahead and continue using our information we've been able to gain so far through conservation of energy. And we're going to modify our equation to now solve for the magnitude of the momentum of the electron. And again, I'm going to go ahead and do some copying and pasting because it makes life so much easier to do it like this. Now, what do I need to modify? I can get rid of this top line here. That's not needed. Probably can even just use a Control K. Yep. Perfect. We end up getting that. I could probably get rid of this. Sorry, guys. You guys got to watch me do a little bit of editing here. It's equal to and equal. Basically those, but I need to take the negatives of them now. Let's see what this looks like. I hope this is correct. All right, so far so good. Let's see if you guys can see what I'm seeing. So basically, I continue from the very last line above, where 0 is equal to the sum of the individual momentums, and I've derived the equation below by basically just moving the momentums of the neutrinos moving the momentum of the electron to the left-hand side of the equation, and then taking care of the negative sign that we end up getting on the momentum of the electron and moving it back over. Now note, these are vectors. So the key thing to note here is that whenever you see a negative sign in front of a vector, all you're basically doing is changing the direction of the vector. And so now what I'm going to go ahead and do is I'm going to factor out the negative sign, and we're going to get some very interesting information about this. So parentheses, copy and paste, put a plus sign. There we go. And so basically what we get is this. We're going to sum our neutrino vectors and get a resultant vector. And it just so happens that the magnitude of the resultant vector that will be in the opposite direction of, well, I'm sorry, that's coming out wrong. Basically, the momentum vector for the electron will have the same magnitude as the resultant vector of the sum of the two neutrino momentum vectors, but it will be in the opposite direction. And so, I'm running really low on time here. So, to kind of make a long story short, we could go ahead and establish some very complicated scenario where we have our muon, it decays and it produces the electron in the two neutrinos, and their momentum vectors are in three-dimensional space. But because we're only concerned with the magnitude of the electron's momentum vector, we can actually reduce the problem to just simply being in one dimension. And I had some math here to show how that works out, but given the time constraint right now, I'm not going to go through all that. I didn't realize it would take me this long to get to this point. So I apologize, guys. Yes, Larry of the G Cloud, you are perfectly right. Hello, Binary Ablaze. Welcome to the stream. And Uncle Bill joined us. Nice for you to join us. Thank you for coming by. But Larry the G Cloud has actually answered the question perfectly. What I was basically going to get at was that the electron's maximum energy will be in the condition where the momentum vectors of the neutrino, of both neutrinos, is in the same direction, and of course the electron, of course, its momentum vector is conserved, and that actually yields the maximum kinetic energy for the electron. But let's go ahead and continue from here, though. So now that we have this bit of information, we can go ahead and we can go back to our conservation of energy equation. And we're going to do a slight modification to it. So let's do that. Indent. So back to conservation of energy. And again, I'm going to go ahead and copy and paste. And so I'm not too sure if someone said this earlier. Let's make sure you guys can see what I'm seeing. Perfect. I'm not too sure if someone said this earlier. But, so yeah, I think, thank you, Michael. Perfect. You came in at the perfect time with that. And yes, no calculus today. Sorry about the last stream. That was some bit of calculus there. But neutrinos, as you mentioned, Michael, they travel very close to the speed of light, and they have very low mass. And that's very important to our equation here, because we can go ahead and drop all the terms that have we can drop the terms that explicitly state the mass of the neutrinos, and in doing so, we obtain the following. So copy and paste. Let me try to quickly work through that. So the rest mass energies, of course, can disappear. Wait a second. Oh no, that's right. All right, so all of that can disappear. Where is it? It's right here. That can go away. So can this. I hope I've deleted things appropriately. Let's scroll down. I think that looks about right. Perfect. All right, so and so basically we get to this point of our equation, and wherever we see a square root and a square, those will cancel out. Which will just basically yield plus the momentums times the speed of light. Sorry guys if it seemed like I'm kind of rushing through this. And so now we can go ahead and we can, and basically you're going to see what the little neat thing that I'm doing here. We can go ahead and we can factor out C within the last two terms on the right hand side of the equation. So factoring out a C, we basically get the sum of the momentums for the neutrinos. All right. And because these are just simply the magnitudes of those of their momentums, we already know from earlier from the conservation of momentum that their sum must be equal to the magnitude of the of the momentum of the electron. And so everything reduces out to being something very nice to work with. All right. Oh man, I'm really running out of time here. All right. So basically, the objective of what I would want to do here is I would want to go ahead and solve for the momentum of the electron. Let me check comments to make sure I'm not missing anything. All right. And so quickly doing that, what we end up getting is, sorry guys, I'm just trying to quickly do this in my head so that we could move on. All right. I think I'm going to go ahead and skip some steps to kind of make this go faster. So moving over the rest mass energy of the electron and moving over the kinetic energy of the electron as well, which is kind of represented by c times its by the electron's momentum. All right, so that's going to be a minus sign. That goes to that. That does that. We're left with this square root. Okay. Upon squaring both sides, we end up getting the following. So we'll get a squared plus, and you guys can probably see what I'm doing here actually. I think I've modified the stream so that you guys can see my editor. And then we're going to get a cross term. Or we're going to get some cross terms actually. We also get that, we get this squared as well. Now I know what my professors felt like when like class was getting ready to end and they were at the board and they were just writing away. But at least with them, it could be like, hey, you know what? We'll continue this during the next class. And I might actually just have to do one of those numbers, unfortunately. All right, let's make sure that everything came out. Wait, I'm missing another term or two. That looks good. I'm missing two terms, it looks like, actually. And they have twos on them. That's right. So I have another term. I think, is it positive or negative? I have two negative terms, it looks like I'm missing. So, and it's going to be a 2 minus a 2. Sorry, guys. So one term I'm missing is the product between the energy. All right. It's now 1 o'clock. And I feel bad I couldn't actually get through all of this. But basically, what we end up getting is that the maximum energy for the electron should be somewhere around 53 MeV, where MeV corresponds to mega electron volts, which is a unit of energy. But basically, you could continue along this path of solving for the momentum of the electron using the line of logic that I'm currently walking through right now. And once you've done that, you plug it into the equation for solving for the kinetic energy. So yes, actually that's a good idea. What I can basically do is pick up where I left off at here, do a part 2 next week, finish this off, and then we can jump into a completely new problem. But guys, if there's something you guys want me to talk about, by all means, like send it to me or just bring it up here, and I'll find a problem or work up a problem that we can, discuss. Don't worry, Guido. You were doing your own bit of physics, and when you were cooking. Hey, what did you cook? If you did any bit of boiling, I mean, that would be convection, and that's physics. But actually, I think for my problem next week, it might be more closely related to astronomy versus physics. But Larry of the G Cloud. Let's see. A muon near rest will decay to three particles plus the momentum of these three. Yes. But a muon moving fast will decay to three particles plus the original. Yep, that's right. So that's exactly correct. If a muon is actually in motion, whatever kinetic energy it had, it would well, it would transfer that kinetic energy to the resulting particles. That's correct. Yeah, I completely understand you, Larry. I have Spectrum too, and throughout the entire stream, my connection looked like it was going in and out, according to OBS. I kept seeing the green light go from green to yellow to red, and so good luck with that talk with Spectrum. That's right, Peter. Any cooking is physics. Well, guys, thank you for joining me today. And again, like I said, I'm gonna pick this back up next week. But if you guys get the chance, I'm pretty sure today is astronomy cast. It's gonna be at 2 p.m. Central Time, which is in roughly an hour any time zone you're in. Um, is the ratio of the transfer of the extra according to mass. So let me quickly think about that. So the extra energy, as far as conservation of energy is concerned, it's going to have the muon will have kinetic energy, and you'd have to add a kinetic energy term into the equations I was just working on. As to how much it changes the maximum kinetic energy of the electron, it's hard for me to say off the top of my head. But the way in which you'd account for it is you'd simply just add the kinetic energy term into the left hand side of the equation for the muon. And so, I mean, you'd still do the exact same steps I've done here. You just add that extra term into it. So instead of one term, it'll be two terms on the left hand side. All right, guys. Again, thank you for joining me. If you guys can catch a astronomy cast, at 2 p.m. Central Time, which is in roughly an hour from now. And I believe also Joe's going to be on tonight. So if you get a chance, check him out as well. Joe, if you're in the chat, could you please let everyone know? Thank you, Susie. All right, guys. I'll see you guys later. All right, bye.